October 10th, 1943. The skies over Munster, Germany. 75 American B-17 bombers set out on what should have been a routine bombing mission. By the time they limped back to base, 30 planes were gone. Vanished. The 100th bomb group was nearly annihilated. 12 out of 13 aircraft destroyed in a single afternoon. They would forever be known as the Bloody 100th. Your odds of surviving 25 missions as a B-17 crewman at that time? 1 in 4. The American daylight bombing campaign over Europe was collapsing. Tens of thousands of young men were dying. And back in Washington, the military brass was running out of excuses. Their theory, that heavily armed bombers could protect themselves without fighter escorts, was being written in the blood of American airmen over German cities. But thousands of miles away, in a California factory, a metallurgist was breaking every rule in the book. He was working with an aluminum alloy that the military establishment had dismissed. An alloy with properties so extreme, so unusual, that conventional wisdom said it couldn't work for combat aircraft. His name wasn't famous. His work was buried in technical specifications and factory reports. But what he created would change everything. Because when his forbidden alloy finally made it into the air, wrapped around a Rolls-Royce Merlin engine in a fighter called the P-51 Mustang, it would turn the tide of the entire air war over Europe. This is the story of how one material, a carefully guarded formula of aluminum, copper, and magnesium, gave American fighters the strength to dive at speeds approaching 500 miles per hour, the durability to escort bombers all the way to Berlin and back, and the structural integrity that German engineers thought was impossible. This is the story of the alloy that won the war. To understand why this alloy was so revolutionary, we need to go back to the beginning of aviation itself. In 1903, when the Wright brothers achieved powered flight at Kitty Hawk, their aircraft was made of wood and fabric. Ash wood for the frame, muslin cloth for the wings. It weighed about 600 pounds and flew for 12 seconds. Wood was light. Wood was easy to work with. And for the first decade of aviation, wood seemed like it would always be the material of choice. But wood had fatal limitations. It rotted in moisture. It splintered under stress. It burned easily. And as aircraft grew larger, faster, and more complex, wood simply couldn't handle the loads. The Great War accelerated everything. By 1915, German engineer Hugo Junkers was experimenting with all-metal aircraft. His first attempt, the J-1, used a steel skin. It was incredibly strong. It was also incredibly heavy, earning it the nickname the Flying Tin Can. But Junkers understood something crucial. The future belonged to metal. The question was, which metal? Enter Alfred Wilm, a German metallurgist working in relative obscurity in 1906. Wilm was experimenting with aluminum alloys, trying to create something stronger than pure aluminum, which was far too soft for structural applications. He added copper, about 4%, then small amounts of magnesium and manganese. He heat-treated his samples, bringing them to about 500 degrees Celsius, then quenching them in water. And then something strange happened. The samples he tested immediately after quenching were only moderately strong. Disappointed, Wilm set them aside. But when he tested them again a few days later, they had become dramatically harder, stronger. The alloy had somehow transformed itself over time at room temperature. Wilm had accidentally discovered age hardening, though he had no idea why it worked. The science wouldn't be understood for another 2 decades, but he knew he had something special. He called it duralumin, and it would change manufacturing forever. By 1918, Junkers was using duralumin in his J-7 aircraft. The British bought the patent and used it for airship construction. The French licensed it immediately, and the Americans, who couldn't get the patent, captured German aircraft during World War I, reverse-engineered the alloy at the National Bureau of Standards, and developed their own version. By the 1920s and 1930s, aluminum alloys were everywhere in aviation. But they all shared one critical limitation. They weren't strong enough for the next generation of combat. Aircraft, the speeds, and stresses of modern warfare were about to exceed what even duralumin could handle. By the mid-1930s, aircraft designers faced a fundamental problem. They needed to build faster, stronger, more maneuverable fighters and longer-range bombers. But the aluminum alloys available simply weren't strong enough. The original duralumin, known in the United States as 17S, had a tensile strength of about 380 to 420 megapascals. That's respectable, but it wasn't enough for what was coming. Engineers needed higher strength-to-weight ratios. They needed alloys that could withstand enormous stresses without cracking, buckling, or failing catastrophically. They needed metal that could survive high-speed dives, violent maneuvers, and combat damage. The Aluminum Company of America, Alcoa, had been working on this problem since the late 1920s. Their researchers understood that adding more magnesium to the aluminum-copper formula could dramatically increase strength. The question was how much and how to process it correctly. Around 1930, Alcoa metallurgists developed what they called 24S alloy. The composition was carefully balanced, roughly 4.4% copper, 1.5% magnesium, and 0.6% manganese, with the rest being aluminum and unavoidable impurities like iron and silicon. The magnesium content was the key. At 1.5%, it was significantly higher than the original duralumins, 0.5 to 0.8%, and the results were spectacular after proper heat treatment. Solution: heat treating at about 500 degrees Celsius, rapid quenching, and then aging. 24S alloy achieved tensile strengths exceeding 470 megapascals. Its yield strength, the point at which it would permanently deform, was around 325 megapascals. More importantly, its fatigue resistance was exceptional. It could withstand repeated stress cycles without developing cracks. This was critical for aircraft that would experience thousands of takeoffs, landings, and combat maneuvers. But there was a problem. Actually, several problems. First, the higher copper content made 24S more susceptible to corrosion. Pure aluminum forms a natural protective oxide layer, but the copper-rich phases in 24S created galvanic cells that could corrode rapidly, especially in salt air or humid conditions. Second, the alloy was more difficult to form and work with. The higher strength meant it required more force to shape, more precise heat treatment, and more careful handling during manufacturing. Third, and this was the biggest problem, the military establishment didn't trust it. The Army Air Corps had extensive experience with 17S duralumin. They knew its properties, its limitations, its behavior in service. Switching to a new, stronger alloy meant rewriting specifications, retraining workers, retooling factories, and accepting risks. What if the new alloy failed in service? What if it developed unexpected problems? What if it couldn't handle combat conditions? For years, the military dragged their feet. 24S was available, it was demonstrably superior. But it sat on the shelf while aircraft continued to be built with the older, weaker alloy until one aircraft came along that would change everything. In April 1940, the Royal Air Force had a desperate problem. Nazi Germany was steamrolling across Europe. Britain was running out of fighters. They needed more aircraft immediately. The RAF approached Curtiss Wright, an American manufacturer, about producing P-40 Warhawk fighters under license. But Curtiss was already at full production capacity. They suggested the British talk to North American Aviation, a relatively small California company that had never built a fighter aircraft. The British were skeptical, but they were also desperate. They gave North American an impossible challenge: design and build a prototype fighter superior to the P-40 In just 120 days, a team led by chief designer Edgar Schmood and company president James Dutch, Kindleberger took the challenge. What they created was radical. The P-51 Mustang featured a revolutionary laminar flow wing design that reduced drag dramatically. Its cooling system was ingeniously integrated into the airframe. And critically, it was built almost entirely from 24S aluminum alloy. The fuselage was constructed from 24S sheet aluminum formed into a semi-monocoque structure. The wings used 24S skin panels over 24S stringers and ribs. Even many of the internal components were machined from 24S plate. North Americans metallurgists, working with detailed specifications from Alcoa, understood that 24S's superior strength would allow them to use thinner, lighter structural members while maintaining rigidity. This weight savings could be converted into fuel capacity or performance. But they also understood the risks. S was less forgiving than 17S. If improperly heat-treated, it could be brittle. If the aging wasn't controlled precisely, the strength could be inconsistent. If corrosion wasn't prevented, the structure could degrade rapidly. To solve the corrosion problem, they used a technique called Alclad. This involved bonding a thin layer of pure aluminum to both surfaces of the 24S sheet. The pure aluminum provided corrosion resistance, while the 24S core provided strength. It was elegant, effective, and expensive. The prototype flew on October 26, 1940, exactly 117 days after the contract was signed. Its performance was impressive, fast, maneuverable, and with exceptional range for its size. But there was one catastrophic problem. The original Mustang used an Allison V1710 engine. This American-designed power plant was excellent at low altitudes, but lost power dramatically above 15,000 feet due to its single-stage supercharger. At the altitudes where German fighters and bombers operated, 25,000 feet and higher, the early Mustang was badly outmatched. The RAF took delivery of hundreds of Mustangs and used them effectively for low-level reconnaissance and ground attack. But as a high-altitude fighter, the P-51 was a disappointment. Back in the United States, the Army Air Force showed little interest. They had their own fighters, the P-47 Thunderbolt and the P-38 Lightning. The Mustang seemed like a dead end, except for one man who refused to accept that conclusion. Thomas Hitchcock. Jr. was the kind of man who seemed designed by central casting to be an American hero. Born in 1900 to wealth and privilege, Hitchcock became the greatest polo player of his generation, a sport requiring fearlessness, split-second decision-making, and absolute physical courage. F. Scott Fitzgerald modeled two characters on him, writing that Hitchcock was high in my pantheon of heroes. But polo was just the beginning. At age 17, Hitchcock lied about his age to join the American Ambulance, service in France during World War I. He transferred to the Lafayette Escadrille as a fighter, pilot, and shot down 2 German aircraft before being shot down himself over enemy territory in March 1918, badly wounded. Hitchcock was captured and sent to a German POW camp. He spent months recovering. Then, while being transported to another camp, the 18-year-old pilot stole a map from a sleeping guard and jumped from a moving train. He hiked nearly 100 miles through enemy territory to neutral Switzerland. After the war, Hitchcock returned to America, dominated polo for 2 decades, married a Mellon family heiress, and became a successful investment banker. When World War II broke out, he immediately volunteered for military service. At age 41, he was rejected for being too old to fly combat missions. Frustrated but undeterred, Hitchcock leveraged his connections to become the assistant U.S. military attaché in London, serving as liaison between the U.S. 8th Air Force and RAF Fighter Command. It was 1942. The American daylight bombing campaign was already faltering. Unescorted B-17 and B-24 bombers were being slaughtered over Germany. The Army Air Force brass insisted that heavily armed bombers could defend themselves. The mounting casualties suggested otherwise. Hitchcock thought the bomber generals were fools. He made frequent visits to RAF bases, talking with pilots, observing operations, and learning from British experience. The RAF had already learned the hard way that unescorted bombers were sitting ducks. They'd abandoned daylight raids in favor of night bombing. During one visit to RAF Duxford, a development and testing facility, Hitchcock saw something that changed everything. A P-51 Mustang fitted with a Rolls-Royce Merlin engine. The idea of mating the P-51 airframe with the Merlin engine came from several sources almost simultaneously in early 1942. In Britain, Rolls-Royce test pilot Ronald Harker flew an early Mustang with its Allison engine and immediately recognized the aircraft's potential. He wrote in his report, "With a powerful and good engine like the Merlin 61, its performance could be outstanding." The RAF agreed to experiment. They took a standard P-51 and replaced its Allison engine with a Rolls-Royce Merlin 65, a two-stage Sandhoud two-speed supercharged V12 that produced about 2,500 horsepower and maintained that power to much higher altitudes. The results shocked everyone. The Merlin-powered Mustang achieved a top speed of 441 miles per hour at 24,000 feet. Its rate of climb improved dramatically. Its service ceiling exceeded 41,000 feet. At high altitude, it was faster than anything the Germans had, except their jet prototypes. But speed wasn't even the most important improvement. The Merlin's fuel efficiency, combined with the Mustang's enormous internal fuel capacity and low-drag airframe, gave the fighter an unprecedented range. With drop tanks, a P-51 could escort bombers all the way to Berlin and back, a round trip of over 100 miles. No other Allied fighter could do that. The P-47 Thunderbolt was tough and powerful, but had limited range. The P-38 Lightning had good range, but struggled at high altitude in the cold European weather. The Supermarine Spitfire was a superb dogfighter, but couldn't fly deep penetration missions. The Merlin Mustang combination was exactly what the 8th Air Force needed. Hitchcock immediately recognized this. He bombarded Washington with reports, test data, and increasingly urgent recommendations to adopt the Merlin Mustang for bomber escort duty. The response from Army Air Force headquarters was polite indifference. General Hap Arnold, the commanding general of the Army Air Forces, had built his reputation on the doctrine of strategic bombing. Admitting that bombers needed fighter escorts was, in his mind, admitting failure. He didn't want to hear it. Moreover, the P-51 wasn't an Army Air Force project. It had been designed for the British. It used a British engine. In Arnold's view, it was a bastard aircraft with no constituency in the American military establishment. Hitchcock refused to give up. He flew to Washington repeatedly. He arranged demonstrations. He used his extensive network of contacts to reach decision-makers. He took his case to Robert Lovett, the Undersecretary of War and Arnold's civilian superior. Lovett, who had flown British aircraft during World War I, immediately understood what Hitchcock was saying. He put pressure on Arnold, reluctantly. Arnold authorized procurement of 2,200 P-51B models with Packard-built Merlin engines in late 1942. It was designated the highest priority. Then he did almost nothing to expedite production. Through 1943, Mustang production lagged. The aircraft arrived in small numbers, too few to make a difference. Meanwhile, the bomber offensive ground on, hemorrhaging crews and aircraft. August 1943, mission to Schweinfurt. 60 bombers lost. October 1943, mission to Munster. 30 bombers lost. October 1943. Second mission to Schweinfurt. 77 bombers lost. The American daylight bombing campaign was on the verge of collapse, and the one aircraft that could save it was sitting in factories, waiting for parts and priority that never seemed to materialize. Hitchcock was furious. He made trip after trip to the United States, hectoring, cajoling, and demanding that P-51 would production be accelerated finally. In late 1943, the Mustangs began arriving in substantial numbers. The first units equipped with P-51Bs became operational in Europe in November and December. January 11, 1944, would prove what they could do. The mission target that day was a Focke-Wulf aircraft factory deep inside Germany. The bomber stream faced a long flight over hostile territory. Everyone expected losses, but this time was different. As German fighters rose to intercept the bombers, they encountered something they'd never seen before. American fighters operating hundreds of miles inside the Reich. Major James Howard, flying a P-51B, found himself alone defending an entire bomber formation when his squadron was separated during the engagement. For more than half an hour, he single-handedly attacked wave after wave of German fighters, Focke-Wulf 190s and Messerschmitt 109s. The German pilots were utterly baffled. No Allied fighter had ever penetrated this deep into Germany before, and this single aircraft was outmaneuvering them, outdiving them, and seemingly unable to be shaken. Howard's aggressive flying saved the bomber formation. Not a single B-17 from his group was lost that day. He would later receive the Medal of Honor. But Major Howard's heroism was built on a foundation of aluminum, copper, and magnesium. Every violent maneuver that day, every high-speed dive, every tight turn pulling multiple Gs, every shuddering burst of machine gun fire put enormous stress on the P-51's airframe. The wings flexed. The fuselage twisted. The entire structure absorbed and distributed forces that would have torn apart aircraft built from older, weaker materials. The 24S aluminum alloy structure held every time. When Howard dove at speeds approaching 500 miles per hour, the wings didn't flutter or fail. When he pulled out of dives with crushing G-forces, the fuselage didn't buckle. When cannon shells damaged sections of his aircraft, the structure maintained enough strength to get him home. This wasn't luck. This was materials science. The 24S alloy's superior tensile strength meant that the Mustang's skin panels could be thinner and lighter while maintaining rigidity. The excellent fatigue resistance meant that stress cycles didn't create cracks that could propagate catastrophically. The carefully controlled heat treatment meant that the alloy's properties were consistent throughout the structure. And critically, the Alclad protective coating meant that even after months of operation in harsh European weather, exposed to rain, snow, humidity, and corrosive exhaust gases, the structure retained its strength. German metallurgists studied captured Mustangs with intense interest. They were shocked by how thin the American aircraft's skin was. They couldn't understand how such a lightly built structure could be so strong. The secret was the alloy. By February 1944, P-51 Mustangs were arriving in large numbers. They quickly became the dominant escort fighter over Europe. Their combination of speed, range, and altitude performance was unmatched. The bombing campaign that had been dying in late 1943 roared back to life in early 1944. Bomber losses dropped dramatically. American fighters began actively hunting German fighters, not just defending bombers, but seeking them out and destroying them in the air and on the ground. Hermann Göring, the Luftwaffe chief, later said in a post-war interrogation, "When I saw Mustangs over Berlin, I knew the jig was up." By June 1944, the Allies had achieved air superiority over Europe. The Normandy invasion was possible because Allied fighters controlled the skies. Soldiers landing on the beaches looked up, and knew that any aircraft they saw would be friendly. The P-51 Mustang was the single most important factor in that air superiority, and the 24S aluminum alloy was the material that made the Mustang possible. So what made 24S aluminum alloy so special? Why could it do things that earlier alloys couldn't? The answer lies in the atomic structure of the material, in processes happening at scales of billionths of a meter that weren't fully understood until decades after World War II. Pure aluminum is soft, very soft. You can bend it easily with your hands. The reason is that aluminum atoms arranged in a crystal structure can slip past each other relatively easily when stress is applied. The atomic bonds break and reform, allowing the metal to deform plastically. To make aluminum strong, you need to prevent those atoms from slipping. You need to create obstacles at the atomic scale that block dislocation movement. That's where the alloying elements come in. When you add copper and magnesium to aluminum and then heat-treat the alloy correctly, something remarkable happens. The copper and magnesium don't just dissolve uniformly in the aluminum. They form tiny precipitates, clusters of atoms just nanometers in size. In 24S alloy, the key strengthening precipitates are called S-phase, Al2CuMg. These precipitates are coherent with the aluminum matrix, meaning their crystal structure aligns closely with the surrounding aluminum atoms. They're incredibly small, perhaps 10 to 50 nanometers across, but they're everywhere throughout the material, separated by just tens of nanometers. When stress is applied to the alloy and dislocations try to move through the crystal structure, they encounter these precipitates. The dislocations can't easily cut through them or bypass them. They get tangled and pinned. This is precipitation hardening, and it's extraordinarily effective. The higher magnesium content in 24S compared to the earlier 17S alloy meant more S-phase precipitates formed during aging. More precipitates meant more obstacles to dislocation movement. More obstacles meant higher strength. But here's the critical part. Achieving this microstructure required precise control of heat, treatment, and aging. The alloy had to be heated to about 500 degrees Celsius to dissolve the copper and magnesium atoms uniformly in the aluminum matrix. This is called solution heat treatment. Then it had to be quenched rapidly, plunged into cold water, to freeze that uniform distribution of atoms in place. Then, and this was the tricky part, it had to age. During aging, either at room temperature over several days or at elevated temperature for a few hours, the copper and magnesium atoms would diffuse through the aluminum matrix and cluster together to form those nanoscale precipitates. If the aging was too short, the precipitates would be too small and too few. The alloy wouldn't reach its full strength. If the aging was too long, the precipitates would grow too large and lose coherency with the matrix. The alloy would become softer, a condition called overaging. The metallurgists at Alcoa and North American Aviation had to hit a precise target, and they had to do it consistently on thousands of sheet metal panels in a wartime production environment with quality control challenges and material shortages. The fact that they succeeded is a testament to the skill of American metallurgists and production workers. Archaeological studies of crashed P-51s have confirmed this. When researchers examined aluminum alloy samples from P-51 Rex decades after the war, they found that the microstructure showed the hallmarks of properly treated 24S alloy: fine, dispersed precipitates, elongated grain structure from rolling, and evidence of the Alclad protective coating. Even after crashes, after years in the ground, after corrosion and damage, the underlying structure of the alloy remained visible. The material that had carried American pilots through thousands of missions was still recognizable. The term forbidden alloy might seem like hyperbole, but in an important sense, 24S really was forbidden, or at least restricted by bureaucratic resistance, institutional inertia, and the military's reluctance to adopt new materials. It wasn't that the alloy was illegal or classified. It was that the establishment didn't want it. It challenged their assumptions. It required changes to their procedures. It forced them to admit that their existing materials weren't good enough. For years, 24S sat on the shelf while men died in aircraft built from inferior materials. It took desperate circumstances, a catastrophic failure of the bomber offensive, and the relentless advocacy of people like Tommy Hitchcock to force the system to adopt it. And even then, it happened too slowly. If P-51s with 24S alloy structures had been available in large numbers in early 1943 instead of early 1944, how many thousands of lives might have been saved? We'll never know. But we do know that once the Mustang reached operational units in sufficient numbers, the course of the air war changed almost immediately. By war's end, more than 15,000 P-51 Mustangs had been produced. They served not just in Europe but also in the Pacific theater, where their range was even more critical. They flew from islands to escort B-29 bombers to Japan, missions of over 1,500 miles. The P-51's combat record is staggering. Mustangs destroyed about 4,950 enemy aircraft in air-to-air combat, and another 4,131 on the ground, more than any other Allied fighter in the European theater. But the story doesn't end in 1945. The 24S aluminum alloy pioneered. For the Mustang evolved into the modern 2024 aluminum alloy. It's still used today, 8 decades later, in aircraft construction, particularly for fuselage skins, wing skins, and structural components. The principles of precipitation hardening discovered and refined for 24S became the foundation for an entire family of high-strength aluminum alloys. The 2000 series, the 7000 series, all rely on carefully controlled precipitation of intermetallic phases to achieve strength far beyond what pure aluminum can provide. Modern aircraft, from the Boeing 737 to the F-22 Raptor, use descendants of the alloy that first flew in the P-51. Mustang, and the broader lesson remains: materials matter. The performance of any vehicle, any machine, any structure is ultimately limited by the properties of the materials from which it's built. The engineers who designed the P-51 created a brilliant airframe. Rolls-Royce created a brilliant engine. But without the metallurgists who developed 24S aluminum alloy and figured out how to produce it reliably at scale, none of that genius would have mattered. Materials science doesn't get the glory. It doesn't get the headlines. The men who developed 24S alloy are forgotten. Their names appear only in dusty technical reports and archived company documents. But their work changed history. Tommy Hitchcock never saw the Mustang fulfill its destiny. On April 19, 1944, just months before D-Day, he was killed when the P-51 he was test flying crashed in England. He was 44 years old. His funeral was attended by military leadership from both the United States and Britain. But the greatest tribute to Hitchcock wasn't the eulogies or the honors. It was what happened in the skies over Europe in the months that followed. When Allied soldiers landed on the beaches of Normandy on June 6, 1944, they looked up and saw swarms of Allied aircraft. Mustangs dominated the sky. German aircraft were almost entirely absent. The air superiority that made D-Day possible was built on many factors: pilot training, tactics, logistics, intelligence. But at the foundation was an aircraft made possible by a metallurgist's breakthrough in understanding how aluminum, copper, and magnesium atoms could be arranged to create strength that seemed impossible. The P-51 Mustang was more than a weapon. It was a demonstration that materials science could change the outcome of wars. That understanding the structure of matter at the atomic scale could translate into dominance at the scale of continents. The forbidden alloy that the establishment resisted became the standard by which all other aluminum alloys were measured. And the fighter it made possible became the standard by which all other fighters were judged. In the end, It wasn't just better pilots or better tactics that won control of the skies over Europe. It was better materials, and the metallurgists who created them.